We're going to apply the conservation of mechanical energy to a couple of pendulum problems. Here's the first one. A pendulum has a speed of 3.0 meters per second when it is at its lowest point in its swing. How high can the pendulum reach? So I'm going to draw a little bit of a diagram here. This is a pendulum. It's an object attached to a string that is swinging back and forth. So the question says at the lowest point in the swing, which I have drawn here, the speed is 3 meters per second. And it's asking us how high can the pendulum reach. So as the pendulum swings back and forth, there's some kind of a maximum height that the pendulum reaches on either side. And we're asked to find how high this is. And I'm assuming they're asking how high it is compared to the lowest point in the pendulum. All right, so that's a diagram there to show what's going on. And to solve this, what I'm going to do is apply the conservation of mechanical energy. The conservation of mechanical energy says that the mechanical energy at any one point, so I'll call it ME1, is going to stay the same throughout. So it's going to equal the mechanical energy at any other point, which I'll call ME2. So the 2 points I'm referring to for this problem would be 1, the pendulum at its lowest point, and 2, the pendulum at its highest point. When you calculate the mechanical energy at both places, they better be equal according to the conservation of mechanical energy. So mechanical energy is kinetic energy plus potential energy. So I'll just change ME to K plus U. All right, and then there's 4 terms right now in this equation I have here. And in this problem, I'm going to actually cross out a couple of these terms because going back to the diagram here, first of all, I need to set a reference height. Anytime I'm dealing with gravitational potential energy, I need to set a reference height where I'm calculating all my heights from. And the simplest thing to do would be to set the reference height right at the bottom of the swing. So I'll call this a reference height. And by doing that, that means the height at the bottom of the swing is 0 meters. And the speed at the bottom of the swing is 3 meters per second. I'm going to add a subscript of 1 there. Okay, so V1 and H1 will be used to calculate ME1. And then at the highest point of the swing, H equals question mark, I'm going to add a subscript of 2 there. So that's my second point that I'm considering this pendulum at. And what is the speed? So what's the speed of the pendulum at its highest point? Well, when the pendulum is swinging back and forth, when it gets to its maximum point, it actually stops for a split second and then changes direction. So the speed at the highest point is actually 0 meters per second. And that's going to allow me to actually cross off K2. It's going to be 0. The kinetic energy at point 2 is going to be 0 because the speed is 0 there. Similarly, what about at point 1? Well, the height is 0 at point 1. So that means the gravitational potential energy is 0 at point 1. Okay, so that simplifies the equation. I'm going to keep going. So K1 can be rewritten with the formula for kinetic energy, which is half mv1 squared. equals, on the other side, I have U2. U2 can be replaced with the formula for gravitational potential energy, mgh2. And then I rearrange the equation for what I need. So what I'm looking for is h2. So I'm going to divide both sides by mg. Divide both sides by mg to get h2. So it's going to look like this. mv1 squared over 2mg. So instead of writing a half in front, I just wrote a 2 in the denominator. And you may notice that there's an m in the numerator and in the denominator as well, so they cancel out. And it's a good thing that they cancel out because I did not give you the mass in the question. Okay, you read the question again. No mass was given. So usually when no mass is given, usually what happens is it does cancel out when you do the math. Okay, now I'll just fill in the values. So in the numerator, v1 squared is 3 squared. In the denominator, 2g, so 2 times 9.8. I can calculate that out in the calculator. And I get 0.46 meters. Okay, so as a statement answer, I can say therefore the max height the pendulum reaches is 0.46 meters above its lowest point. So there's an example of a pendulum question applying the conservation of mechanical energy. The next one is very similar. It's just asking the opposite. So it says that the highest point of a pendulum swing is 1.5 meters higher than its lowest point. What is the speed of the pendulum when it reaches the lowest point? So I'm going to draw a similar picture. So we'll have a pendulum, but now the pendulum starts at the highest point. Okay, so that's the highest point in the pendulum. It's going to swing. It's going to swing, and eventually it will reach its lowest point at some point. It'll swing through and come back. But this is what I'll draw. So at its highest point, it says that the height is 1.5 meters higher than its lowest point. So what I'm going to do is, again, I'm going to set the reference height at the lowest point. I think that's the easiest. Reference height. So if I set that to be the reference height, then the height at the starting point, h1, is 1.5 meters. And the speed at the starting point is 0 meters per second. Remember, at the highest point of a pendulum swing, it is at rest momentarily. So this is going to swing down and reach its lowest point. So the lowest point has a height, h2, of 0 meters. And the question is, what is the speed at the lowest point? So v2 will be a question mark. And it's the exact same setup as before, pretty much. Maybe the 1s and 2s got interchanged, but that's not really going to change the concept that mechanical energy is conserved. ME1 equals ME2. Yeah, that's the main concept there. Mechanical energy is kinetic plus potential. And what gets crossed out this time, well, the way I've labeled it h2 equals 0 meters. So height 2 is 0. That means gravitational potential energy 2 equals 0. And then what else equals 0? I labeled V1 as 0. So the speed at point 1 is 0. That means the kinetic energy at point 1 is 0. So those become 0, and now I'll keep going. So the equation for U, or gravitational potential energy, is mgh. And then on the other side, the formula for K, kinetic energy, is half mv squared. This time I am solving for V2. I'm solving for V2. So what I'm going to do is multiply both sides by 2. That's kind of like moving the half over. I multiply both sides by 2 and divide both sides by m and square root both sides as well. So it's going to look like this. Multiply by 2, divide by m, square root. Just like last time, there's an m in the numerator and denominator, so they cancel out. So I'm just going to rewrite this a bit neater. It's going to just be the square root of 2g h1. I can fill in the values. And I should get an answer that's bigger than 3, because the previous question, the speed at the bottom was 3, and that only reached a height of 0.46 meters. This one has a height of 1.5 meters. So it starts off higher, so the speed at the bottom better be bigger than 3. I'll do it in the calculator, and I'm getting 5.4 meters per second. All right, so that's applying the conservation of mechanical energy to a pendulum. And you're allowed to apply the conservation of mechanical energy. That question was discussed in the Google form from the previous lesson, actually. All right, there's going to be one more video on a roller coaster style question, and then we'll get you practicing on your own.